Hello and welcome to my talk on 32-bit Linux. My name is Arnd Bergmann and I'm the maintainer for the SoC tree in the kernel and also for new architectures getting merged and old architectures getting removed sometimes out of the kernel. So I know quite a bit about the 32-bit side. Let me start by making it very clear. 32-bit is obsolete from a new product perspective. The only reason to still use it is if you have existing software, existing hardware that you need to support. And about once a month, I see somebody ask, like senior kernel developers asking, can we just get rid of 32-bit right now, please? So I think we need to talk about this with more specific looks at what parts of 32-bit are obsolete, which parts we would remove in the near or distant future, which parts we will certainly still need for a while, and why this is. For this, I have grouped the platforms that we support in the kernel into 5 different categories, and we'll look at each one of those separately because they're quite different. The one that most people immediately think of for 32-bit, at least the older ones of us, are the desktop machines, desktop server machines that everybody had. So if you've been around in the 90s, you probably had a 32-bit machine. Probably one of these. These are all the non-embedded machines that a Linux 6.16 kernel would, in theory, run on. The red ones are the ones that we no longer run on. Then you can see on the bottom we have the old Unix RISC ecosystem, which moved over to 64-bit just after a few years of having 32-bit RISC. So 30 years ago, the entire Unix ecosystem moved over to 64-bit. And then 20 years ago, the same thing happened on the PCs, so x86 and the associated things, PowerPC, Apple, they all changed to 64-bit about 20 years ago. The one outlier that we had on the, let's say, consumer or general purpose side were things like Chromebooks and, of course, Android phones, which are somewhat embedded, but they're also like PC-like in the sense that you can install your own software and you are in control, which you're not on most embedded systems. So those happened 10 years ago, and obviously we still have them to a certain degree. If this was all that we had in Linux, we would have removed 32-bit support a while ago. But since embedded Linux exists, and that's what we're all here for, these can still be in the kernel without causing additional problems. So looking at the embedded side, also around 10 to 15 years ago, ARM pretty much took over the entire embedded market. We used to have something like 10 different architectures that were in widespread use. The thing that happened just this year for the first time is that we support more ARM v8 compatible machines in the kernel with device tree files than we have support for ARM v7 machines. So up until Linux 6.14, there were more ARM v7 machines than anything 64-bit in terms of embedded machines. This only changed this year. If you look at the entire thing, it's 90% ARM. So we have support for around 3,000 machines on any of the ARM architectures. Anything older than ARM v7 is this bit below. That's ARM v4, v5, v6 together, and then all the rest pretty much doesn't matter. Like in terms of size, not in terms of I have this device and it matters very much to me. Looking just at everything that came before ARM v7, we have around 30 distinct SoC families where You can take a modern kernel, you can take a device that you bought 10 or 20 years ago, and in theory, you can put the kernel on and it still works. That's the idea, where we have support in the kernel today. There are only 3 of them where you still get new chip releases. We have the x86 line, we have the X-Burst MIPS chips, and the microchip SAM9 ARMv5 family. Everything else has gone out of production, out of marketing, but Linux still supports it beyond the commercial life of the chip. In some cases, you can still buy the chips, even though the manufacturer doesn't make them anymore. In most cases, the manufacturer has stopped making them, marketing them, and supporting them many years ago. And what you can see, the darker colors, is where this chip used to be the only thing that was available. So if you look, for example, at Anyway, doesn't matter. So the darker ones, I can't read it myself. And the important bit are the colors here. So the darker colors are where the ARMv5 or MIPS32 was the only thing that was available. The lighter colors are the modern world, where there is an ARMv7 replacement, and you will see that almost everything, whether it was PowerPC, MIPS, ARM, v5, has an ARMv7 replacement now. In some cases, like on IMX, which started out with ARMv4, we went all the way from v5, v6, v7, v8 to ARMv9. And you can go further back to the Motorola Dragon Ball, and all in the same product family. So this is pretty much 40 years of one family. And we still support the IMX2, which has users and people still update kernels on those machines, which is really the interesting bit. So we don't care about a PowerPC machine that was shipped 20 years ago and has never seen a kernel update. So for the purpose of a kernel maintainer, the only thing that really matters is, do we still support this with future kernels, because users rely on kernel updates. Some product lines disappeared, so if it's white here, you will see that the product line is no longer around. So around a third of these are still in production, and there is an ARMv7 or v8 based replacement. And we still support those. And around 10 years ago is when a lot of these chips moved over, because the Cortex-A9 was just so much better than most of the other CPU cores at the time. So everything changed over to the Cortex-A9, and then they moved on to Cortex-A7, Cortex-A53, or something beyond that. And then there's probably about 10 SoC platforms where today we can raise the question again, should we remove them? So what you can think of here for the really old platforms is not a specific lifetime as you would expect, where you say, well, after 10 years or 20 years or 25 years of support in the kernel, this is clearly too old and has to go away. The way I like to think of it is more of a half-life. So within 5 years, we might remove half of the platforms. I asked the question 5 years ago, what should we remove? And then we did remove quite a number of old platforms, and it's probably time again to remove some of the ARMv5 platforms, also some of the ARMv7 platforms that clearly have no remaining users. And we need to keep asking that question, because supporting something when there are no users is just a waste of time. Supporting something when there is users, obviously, is very important to those users. This is a chart of all the ARMv7 boards that we support and when they got merged into the kernel. So the colors show the different types of CPU cores and or SoC families. One thing you'll notice is that well, first of all, the numbers are going down quickly. 5 years ago, we were still merging 32-bit ARM boards at the same rate as 64-bit ARM boards, and this has completely stopped. So now 32-bit new support is outnumbered by 64-bit, probably 10 to 1. And you can see this reflected in this line, in the total line going down. You'll also notice that everything now is the Cortex A7 for new chips, or the NXP IMX6, which is just this yellow thing. This is just one chip family from one vendor that is just super popular in industrial devices and gets deployed everywhere. Most of the users have moved on to IMX8, so 64-bit, but there's still enough coming in that this family alone makes up about a third to a half of the new hardware coming in for this year. This is a look at the licensable architectures other than the ones where we support full SoCs. So unlike ARM and PowerPC and MIPS, any of these are probably in something where a company built a fully custom SoC using one of these CPU cores. None of them are mainline in the kernel out of these 32-bit ones. And unlike the others that were replaced by 32-bit ARM and 64-bit ARM, these were all replaced by 64-bit RISC-V. So if you don't care about compatibility with ARM, the only thing left now is 64-bit RISC-V, which is where this part of the industry went. We have absolutely no way of knowing who the users are, because you can't even buy the chips. They are probably somewhere in devices. We don't know. And around 10 years ago, 10 to 5 years ago, every one of those manufacturers announced a RISC-V-based replacement where you can now license a RISC-V compatible CPU core from the company that used to make these other 32-bit cores. And there are more that are no longer supported in the kernel, like NDS. 32 is not listed here because it's already gone from the kernel. These are just the ones that are remaining. Then one thing that I listed separately is the no MMU support. So we have supported no MMU Linux for quite a while in the kernel, and until about 2017, there were always commercial products based on those. With the arrival of Zephyr, this has pretty much stopped. So the only reasons why anybody is still working on these are either to support customers that they already had before 2017, or just to show off that it can be done. Like a student project, you might show, I take this microcontroller, I put Linux on it, and yes, it works. So those are that is all the support that we have. So let's look at what problems it causes. Most of the complaints that we get around still supporting 32-bit come from the file system and memory management people. The number one point is highmem support. So highmem, for those who don't remember, is where you have more than around 800 megabytes of memory supported in your system. But since the Linux kernel maps only the first 800 megabytes, depending on the architecture, directly into its virtual address space, anything beyond that requires special tricks to access. And this is quite complicated, and you need support for it in file systems and device drivers. It's everywhere in the kernel, and we'd like to get rid of it. Sparse mem is another one. It's a minor thing where we still rely on it on 32-bit ARM, whereas most other platforms no longer do it, and it complicates a few things. Then we have the ongoing problem of the 2038 compatibility. I spent years working on that, converting the kernel to use 64-bit time types, and just this year We have a Debian release finally. So this is ongoing. And then we have distro support, which is getting less and less. So a lot of distros, like you could just get Debian for all the 32-bit platforms. You could get all kinds of other distros off the shelf for 32-bit ARM, and they are stopping. One of the things that we are trying to push people to use instead of 32-bit kernels is to run a 64-bit kernel, if at all possible, and then keep running 32-bit user space if you are memory constrained. I actually was quite surprised when I did the measurements, and I found that on a small system where you may have something like 32 or 64 megabytes of memory, which is very small by today's standards, switching from all 64-bit software to all 32-bit software lets you do the same things in almost exactly half the space. So changing the kernel halves the amount of memory that the kernel is used. Changing user space halves the amount of memory that is used by user space. Since most of the memory hopefully is in user space because that's where your application code lies, changing over the kernel has a small cost on 64-bit, whereas keeping user space in 32-bit can make a huge difference if you are at the point where you cannot afford to double your memory. If you can afford to double your memory, charge your customers $1 more, that's fine. If the dollar is making a difference for the product, then using 32-bit user space is still a reasonable solution. But please don't use a 32-bit kernel if there is a 64-bit CPU in there. And unfortunately, all the latest CPU cores from ARM no longer offer this feature. So up until the Cortex A510, there was the option of having 32-bit user space, and now that is gone on the latest cores. But we still haven't seen any low-end embedded chips with just the Cortex A320 or even the A510. We're just about moving from Cortex A7 to Cortex A35, which is the lowest ARMv8 core. So that transition has only happened in the past 3 to 5 years, and it's still ongoing. Highmem, I already said, 800 megabytes. If you have a gigabyte of RAM, you won't suffer from removing highmem. If you have 2 gigabytes, things look different. On 32-bit ARM, we do support a handful of systems that have up to 16 gigabytes, but they are exceedingly rare. And this will die soon. If you have, yes, so this is a chart showing my mental image. This is not an accurate number, but pretty much if you look at 32-bit ARM systems, almost everything has less than a gigabyte. This is the default. There are a couple of systems that have 2 gigabytes. Kinds of gets a little bit silly when you're paying much more for the memory than you pay for the chip. But there are use cases for this. And then 4 gigabytes, there were a couple of Chromebooks that have this, but they have all gone off service 5 years ago, and it would be completely crazy to take such a Chromebook and try to do a presentation at ELC or something like that. And anything more than 4 gigabytes, I hope that we are at the point where we can just not support these at all. If you have systems that have more than gigabytes and you still have to upgrade kernels on these for your customers, I would like to hear from you. There are 3 ideas that we are trying to push for those systems. For a while, Linus Valet has worked on the VM split 4 gig support, where we take, it revives an idea that we had 20 years ago on x86, where you completely split the virtual address space. So you have close to 4 gigabytes of kernel linear addressing, and you have close to 4 gigabytes of user space addressing. It's really hard to actually get it working efficiently. So it's not clear if this will ever see the light of day. If you have systems that absolutely need 4 gigabytes and you have to keep supporting them, we need to talk about who can actually finish this work, get it implemented, get it into the mainline kernel. An easy idea is the dense mem support, as we now call it, replacing the sparse mem support, where we rewire the way the memory management works so that if you have, for instance, 1 gigabyte of memory, but it's not contiguous. Right now, only the first bit is low mem. The second half of it may be high mem, and that goes away. So there are some systems where, even though you have only 1 gigabyte of RAM, you can only use half a gigabyte of RAM. And this would solve that specific problem. This is also under work. I think we need to finish this work before we can remove highmem support, because there are enough users that would benefit from this. But also, I would like to hear if you are one of those. And then for the systems that have 4 gigabytes, if you're not doing the VM split 4 gig, or if you have more than 4 gigabytes, this would be the only thing where we remove almost all the highmem support from the kernel, but leave the bits that are required for having compressed swap. So you can swap into highmem with compression, which gives you access to even more physical memory, or not quite physical memory, like memory that is accessible by a process at the cost of some performance, but still lose all the complexity that is associated with highmem. And there are, so for pretty much any embedded system that suffers from this highmem problem, we would have to come up with individual solutions, sometimes creative, sometimes we can work around it. Sometimes the easiest solution might be to actually replace all those machines of one product line, which is sad. There are other cases, like when I first talked about this about half a year, Pavel Maciek asked, he said, well, his favorite ThinkPad from 2006 has 3 gigabytes and it would only run with 2 or 1 if we do it. So if you can come up here, I'll give you this one as a replacement. Same laptop. This is what I used for years at conferences as my personal laptop. And it's the same laptop with a 64-bit CPU, supports 8 gigabytes. Okay, that's fine. So creativity. This is the only one I have, unfortunately. Right, so these are some examples where I know we have 4 gigabytes, so these will be among the ones that suffer the most. And again, I'm collecting more examples. All the platforms that I know that have more than 4 gigabytes, as far as I know, we can completely ignore. We still support them. These are mainly server chips. Sometimes they're used in high-end networking. Most of these have been turned off years ago. Some just don't get kernel updates. If you have one of these on the right, I definitely want to hear about it, if you're still upgrading kernels. So 2038, a rough timeline. 5 years ago, I completed the work together with Deepa on changing the kernel to U64-bit time-T. The same year, we had muzzlibc. 1 year later, we had glibc, and this year, both Debian and Ubuntu have done commercial distribution, or not commercial, have done binary distributions that include this. If you're using Open Embedded, Yocto, Buildroot, whatever, that has supported it for a while. But this is an important step. There's still a lot more to do. One thing that I keep noticing is packages that just hard-code the types. If you have something that's not written in C, if it's written in Rust or Python, there's probably a 2038 bug in there. Most of the software written in not C these days already has problems running on 32-bit. And then there's ongoing issues with system calls. So anything that uses the FewText system call has like a 50-50 chance of getting it right. And yes, at the moment, we still enable this 32-bit time T syscalls in the kernel for every user. Once we turn those off, we will find a lot more of those bugs. So there's still work that needs to be done. For a reasonably small system, you can just set the time to a future and test it enough that you can be fairly sure that it works. Nobody, as far as I know, has done testing for a larger system that uses a lot of complex software doing all this. So I still would not expect 32-bit desktop operating systems to ever get there and survive 2038. Big-endian, on the face of it, completely unrelated to 32-bit, of course. The main thing it has in common is that a lot of the Big-endian systems are also 32-bit, and they're also obsolete. And there's some other parallels. The main one I see is there's only really one thing holding it all together. So the same way that we have 32-bit ARMv7 making up a large portion of the embedded market still, and keeping everything else alive, because we absolutely cannot remove 32-bit support as long as there's ARMv7. On Big-endian, this is helped by IBM, supporting their mainframes and to some degree their PowerPC servers, where as long as IBM supports these, Big-endian support will be in the kernel. If there is no more commercial interest in keeping Big-endian alive, the questions to remove Big-endian support will suddenly get a lot louder. But this is unlikely to happen anytime soon, of course. These are some things where in the past year we have discussed removing support. I have actually removed support for some x86 machines on the high end. So 32-bit x86 servers with more than 4 gigabytes or more than 8 CPUs are no longer supported because I have shown that nobody had them anymore, or they were already broken. And in the same way, some of the oldest machines with the DEC strong ARM from the late 1990s, I think we should just remove. That also solves some other problems in the kernel where they use old interfaces. The early ARMv6 is OMAP2 and IMX31, those specific SoCs. They complicate everything in the ARM32 architecture, so I hope to just remove them, even though some people still have their Nokia 770s. Anything that's not device tree, I would really like to get rid of in the ARM architecture, and there's only about 30 left, and most of them are early ARMv4, v5 systems. Cortex-M, as I said, the no MMU support doesn't really have any users left, and that has been the case for about 8 years, and I hope that once we've passed 10 years, so 2 years from now, we can remove them and I would start with the Cortex-M ones. So I'll probably start asking questions on the mailing list some point next year, so we can remove them in 2 years. Can't really influence what the other architectures do. The Intel 486 support, we were very close to removing it earlier this year. It hasn't happened yet. I think it will happen soon. And then I sent a series of patches to remove KVM support for 32-bit. I also need to refresh that. I think we found one user on PowerPC, so we'll keep it from PowerPC, but not the others. And that's pretty much it. So to summarize, the same way that we have supported ARMv5 chips that went out of support 10 years ago, I think with ARMv7 boards and chips still coming in, we need at least another 10 years of support for ARMv7. And obviously you might say, well, it could be up to 30 years. You could also say, well, in 5 years, nobody will care. My guess would be 10 years here. So before 2038, but people will still be using those systems after the kernel support is gone. So they would just not keep getting kernel version updates. They might still get bug fixes for a couple of years. So the 2038 stuff is still very important, but not much beyond that. Everything that is not ARMv7 will fade away earlier, most likely. And we'll just keep removing them bit by bit as we find that there are no users left for one of the 30 remaining SoC platforms. Highmem removal, my estimate is that in 2 years' time, it would be gone. So the way I would like to do these removals is to have one LTS release, so the last kernel for a given year would still have support for whatever we remove, and then early in the following year we remove it. So the kernel that gets released late next year would still have highmem and no MMU, and the first kernel for 2027 would not. But that obviously needs debate, and there's lots of opinions on this. And that's it. Thank you very much. Any questions? I think there's a microphone in the back. There's questions. Can you grab the microphone behind the camera?
Yeah, thanks for the talk. I would like to know what are your heuristics to know whether a platform has still people that are involved in it. Maybe you're just looking at patches, but if something is just working, how do we know there are still users? Mm-hmm. And maybe follow-up question, can we improve that?
Right, so this is indeed a hard question, knowing whether something is truly dead or not. For the x86 stuff, I looked at a lot of old web pages to find out what systems actually existed at the time, and I could show that all the ones that did exist are clearly broken already for other reasons. So if we know it's broken, then we know there are no users. That's an easy one. Otherwise, the best approach is ask the people who last touched it. We have the Git history for every single file in the kernel, and what I usually do is I see who did the commits, and I ask them. And they probably, either they know they're using it, or they know somebody who is still using it, or they know for sure it's dead. And unfortunately, in some cases, they don't know either. Okay, next question here.
Big-endian RISC-V?
It's not supported, and I hope that stays that way.
Well,
so the last architecture we merged that was Big-endian is OpenRISC, and that was merged in 2010.
You know Ben is working on it, huh?
I know. I hope he doesn't send it upstream, though. I mean, we have discussed many things for RISC-V in the past. Like, there are many, like, the thing about RISC-V is that anybody can do anything. So they do. Not everything is a good idea. Any other questions? Yes?
How about no mem and no MMU and the newer ESP32?
No MMU and the new ESP32. Yes, that was, I think it has worked for something like 5 years at least. So the patches have been out, and the maintainer has never sent them upstream as far as I know. So there's an out-of-tree support for ESP32. I would consider this one of these toys where, yes, it's cool that it works. It's a lot of fun to get this working. I don't see any practical applications, to be honest. Because anything that you could do within the small amount of memory, you can do better with a smaller operating system. Linux has really gone very, very bloated over the years.
You can add IMX28 to the list. That's ARMv5. It's probably going to be with us for a long, long time.
Yep.
Thanks.
So I think the IMX28 was still being sold last year.
I think it's actually still being manufactured. So there are new chips which you can buy, and they are being taped out.
I don't think there are new chips. I think there's probably an old, like the old mask sets that are still being used. So as far as I know, the only ARMv5 that is still getting new chips is from Microchip, formerly Atmel. So they come out with a new chip every other year.
Let's talk about it afterwards.
And if there's one more question, then I'm not. Well, thank you very much for your questions, your time.